No. Okay, so let's wait 1 minute and then then let us start. So, okay, maybe it's already the time. So, uh, okay, our next speaker, as I said, Fernando Guerrero-Poblete, and with his talk, uniform and completely non-equilibrium invariant states for weak coupling limit type quantum master semigroups. So you have 25 minutes, please.
Thank you very much. Thank you very much. First of all, I would say thanks to the organizer, especially to Professor Vijay. Thanks for the invitation. And thanks for the introducing. This is a joint work with Marco Cruz de la Rosa and Julio Cesar Garcia. Well, the contents of this talk is organized as follows. First, we give the preliminaries about the weak coupling type generators. After that, we restrict our attention to the finite dimensional case and the states associated with currents that have whose associated currents have constant absolute value are the associated with the Eulerian cycles. Finally, we want to describe this kind of invariant states. Okay. The following definitions are due to authors as Saccardi, Fagnola, and Quesada. Let H be a positive and self-adjoint operator in the spectral decomposition. This set is the set of bar frequencies, and B plus is the set of positive bar frequencies. With the subscript, with the B omega, we denote the pair of the set of pairs such that difference of eigenvalues is equal to omega. And B plus omega, the set of pairs such that the difference is equal to omega and is positive. Now, a Markov generator is said to be of the weak coupling type if the generator has the form, the following form. In this expression, we emphasize that the generator is the sum of generators. So it has this form where this is the anticommutator, this is the commutator. When delta omega is a self-adjoint operator and B a linear operator. The constants gamma have this form, and the periodic representation of the for each generator and for any row state is as follows. Is in this way. So this kind of generator is called Markov generator of the coupling limit type. Okay. The following are the theorem 4.1 and proposition 4.1 due to Accardi, Fagnola, and Quesada. The first of all is that for a state that are a function of the Hamiltonian, one has that the pre-dual generator has the following form. Is in this way. where a double bar means the modulus. Now, the case when H has a non-degenerated spectrum is characterized by the condition that all the spectral projections are one-dimensional, and the fact that for each ball frequency, there is one and only one, such that difference is equal to omega. Under the assumption of the spectrum not degenerated, the generator has this form. Now, excuse me. From now on, we are going to positive, and that all these operators are different from zero. Now, we're going to restrict our attention to the finite dimensional case. And we are going to suppose that the spectrum is ordered in this way. So with spectrum ordered in this way, we can write the generator, the preload generator, in this form. Now, in this expression, it's easy to see that sufficing condition for rho to be in the kernel of L is that expression. This is for all I less than J. Such a condition, this condition is known as Littell balance. Now, the aim of this talk is to characterize the invariant states such that for all I less than J, these expressions, this above, the absolute value be a constant D and strictly positive. If D is equal to 0, we have a Littell balance. Okay, in order to do that, we're going to give an bijection between this set of pairs and this subset of integers. And we are going to give a bijection between triplets, this set of triplets, and this set of integers. Is given by this and by this. In fact, this bijection is the lexicographic order. In fact, is that, really is that. Now, it is clear that if the spectrum of H has a dimension n, then this operator has n combinations to sonance. With the bijection given above, and denoting Jk, where k is the scalar, that satisfies precisely this lemma. We can rewrite the generator in this form. This form, we can rewrite the generator. In a matrix form, we can see it in this way. Now, we have this quantity of diagonal matrices from which n minus 1 are linearly independent. The way to be able to see that is the following. We identify the matrices with these vectors, which in a matrix, we can see it in this way. This is the matrix called gamma. Namely, this matrix is is an incident matrix of a directed graph, namely the so-called interaction graph of a Markov generator. Now, we're going to review some classical results in graph theory. The first of these is the following. The rank of an incidence matrix associated with a graph with n vertices is n minus p, where p is the number of connected components. It's easily seen that the rank of the matrix gamma, the matrix above, is n minus 1. So this implies that the kernel has dimension n minus 1 combination 2. This is the kernel, the dimension of the kernel of gamma. We want to give an explicit basis for kernel of gamma in this way. We will denote 3 cycles in this way. A cycle of this form, we will denote it as this, or as this, where R is the mesh of this mapping, the mapping given in the lemma above. 3 cycles like this. For example, this in the case when n is equal to 7, we have this kind of 3 cycles. This one, this one, this one, or this one, and others. Explicitly, this theorem gives us a basis for kernel of gamma. This set of 3 cycles, where we have 1 in the position k of this vector if the cycle passed through the edge k, and have -1 if the cycle passed through the edge k in the opposite direction, and 0 in other case. This is a basis. We have an example of one application of the theorem above. This is the following. With H Hamiltonian in this form, we have so that we have 4 vertices. We have 6 edges, and the kernel has dimension 3. Explicitly, this set of cycles is a basis for the kernel of gamma, of the matrix gamma. Now, we're going to define what we call the uniform and completely non-equilibrium invariant states in the following form. Given the probable generator of a finite dimensional Markov generator, we say that a diagonal invariant state, this is important, diagonal invariant, is uniform and completely non-equilibrium if these quantities, called as currents, in absolute value have the value d. This is one of the most simplest cases of equilibrium invariant states, non-equilibrium invariant states. And this is for all m and n. Okay. Observe that d equal to 0 corresponds with the detailed balance condition, the usual detailed balance condition. Now, these kind of solutions correspond with a cycle such that each enter has the value 1 or -1, and for all k. This kind of cycle are called invariants, and any graph that contains at least one cycle of this type is called invariant. The study of this kind of cycles is well known. That kind of cycles, well, it's related with this problem, Koenigsberg-Bridge problem. Now, another result, classical result in graph theory is the following. A non-trivial connected graph is invariant if and only if each vertex has degree even. This is a well-known theory. So from this result, we can conclude that since we are assuming that the quantum graph is complete, it is invariant if and only if the spectrum has dimension odd. This is a necessary condition for the existence of invariant cycle. Now, the question is how we come to construct invariant cycles. For general case, this is a description of the method to construct a invariant cycle. In our case, we can construct it in this way. We are going to do jumps of size 1, starting off from a vertex, for example, the first, and we finish it on it. Once we do that, we do jumps of size 2. This notation means modulus. And so we can do the same and so on until jumps of size L. We're finishing with concatenating these cycles. So in this way, we can construct a Euler cycle that we will call Euler-Hierhauser, because Hierhauser is the author of this algorithm. As an example, a Hamiltonian, which spectrum has dimension 7. In this case, L is equal to 3, and we start making jumps of size 1, jumps of size 2, and jumps of size 3. Finishing to concatenating these cycles, the cycle 3, the cycle 2, and the cycle 1. This is the Euler-Hierhauser cycle. Pictographically, we can see it in this way. Jumps of size 3. 1, 4, 7, 3, 6, 2, 5, 1. Jumps of size 2, 3, 5, 7, 2, 4, 6, and 1. And jumps of size 1. So we will have this Eulerian cycle. Jumps of size 4, jumps of size 2, jumps of size 3, jumps of size 2, and jumps of size 1. This is the Eulerian cycle. Formally, we can construct an Eulerian cycle in this way.
Sorry, you have 2 minutes. Right?
2 minutes. Okay, let me do it faster. Okay, with this theorem, we can give an explicit expression for the invariant states that satisfies that conditions. Rho will be in this form where the eigenvalues have explicit expression in this way. The first has this form, and the following this form in that cases. Where gamma, alpha, and beta have this form, notice that kind of symmetries. And we finish with a sketch of the proof. The proof is based on this theorem because we suppose that all these currents have the value d or minus d, but we don't know which have this value and which ones have this value. So because of the theorem 9, we can see that have this value in this case and minus d in this case. Well, we can solve these equations to get this, and using the trace condition, we can conclude the theorem with some calculations. And the final calculation is this. And finally, we can get also this expression for the first eigenvalue. Okay, that's all. Thank you very much.
Thank you very much. Any questions or comments?
Maybe I, if possible.
Sure.
In comment on question, my work in PhysRFA in 2011, I considered problem of work is engineering pure and mixed quantum states, and I considered controllability of open quantum systems, which with master equation derived in the weak coupling limit, but with control terms. And one of elements of I showed complete controllability in a set of density matrices, and one of elements was creation of non-equilibrium invariant states, also in the weak coupling limit master equations, when state of the environment was considered as non-equilibrium, non-Gibbs. So when under certain assumptions, it created non-equilibrium states of a system which interacts with the environment in the weak coupling limit kind of master equations. It was one of elements of SEM where there were over coherent control steps, etc. But so is it similar? So do you consider like a non-equilibrium environment and obtain convergence to non-equilibrium states?
So, the question is?
So is it similar? So I considered the case the master equation derived in the coupling limit, and the state of the environment is non-equilibrium. And so when invariant system state is also will be a certain non-equilibrium state. So is it similar in your case? So do you consider effectively non-equilibrium environment to obtain non-equilibrium invariant states of a system. So is it similar or what?
Well, we have not considered yet that case. For us, the non-equilibrium simply means that this quantity is different from zero.
Yeah.
This for us.
So state is non-Gibbs, non-thermal, right?
No, okay.
Yeah,
exactly.
exactly. This is what I considered. Exactly. Okay. Maybe I will send you my reference. It can be interesting.
Okay.
Okay.
I will appreciate that.
Okay. Any other questions or comments? Maybe I have a sort of maybe not directly connected question. I know for the classical Markov chains for reversible classical Markov chains. So in the situation of detailed balance, we have the connection between resistive networks and the Markov chains, and we in particular could calculate some properties of Markov changes by means of resistive networks, because they have the same graphs, but a bit but we have certain we could apply certain manipulation on resistive networks as in our school physics. Is there some analogy in quantum case? Maybe you know, because it is possible to think about resistive networks as some graphs with special sets of manipulations on it, because so it seems to me very close to your work, but I don't know anything about it in quantum case. If you know something about it.
No, I'm sorry, we have no physical examples for this kind of Markov generators. We have no physical examples. I know about this kind of resistive networks in the classical case, but in the quantum case, I'm sorry, we don't have examples, physical examples.
Okay. Well, any other questions or comments? So if no, then thanks the speaker.